We have a working recipe now. Pick a linear model, pick a loss, and slide downhill with gradient descent. It feels like we invented prediction. But there is a crack in the foundation. There are patterns where no amount of data, no clever learning rate, and no patience will ever make a linear model succeed. This episode is about recognizing that wall, precisely. First, remember what a linear model really is. In one dimension, it's a line you slide and tilt. In two dimensions, it is a plane. But for classification, the only thing that matters is the boundary where the model is undecided. In two dimensions, that boundary is always a straight line. That single fact will drive everything today. Now let's build a dataset that is doomed for any straight boundary. Put 4 points on the corners of a square. Label the top left and bottom right as class A and the other two corners as class B. Try to draw a single line that separates A from B. Whatever line you choose, you will always trap at least 1 point on the wrong side. Notice what we are not saying. We are not saying training is hard. We are saying the best possible linear model is still wrong. Even if you had infinite data sampled from this pattern, the model class itself cannot represent the rule. This is a representational limit, not an optimization failure. Let's make that precise with the simplest linear classifier. Take a weight vector and a bias, compute a score, and predict by its sign. The decision boundary is where the score is 0. That boundary is always a hyperplane. So the question, can a linear classifier solve this, becomes can one hyperplane split the two classes with no mistakes? XOR answers, no. Here is a clean way to see the impossibility without hand-waving. Suppose one line separates the classes. Then the two A points must lie on the same side of the line because they share a label. But in XOR, the A points are opposite corners. Any line that puts one corner on a side will put the opposite corner on the other side for some direction. You cannot keep both diagonals consistent with one cut. Now, connect this to loss. If no separating boundary exists, then for any weights and bias, at least 1 point is forced to be wrong. That means the loss cannot go to 0. Gradient descent will still move, and it might find the best compromise, but the floor you hit is not because you stopped early. It is because the model family has a built minus in error. This failure is not rare, it is structural. Anytime the correct boundary is curved, or has multiple regions, or wraps around like a ring, a single line cannot do it. Think of a donut minus shaped class around a center point. A linear boundary always cuts space into two half minus spaces, but the donut needs a boundary that encloses. That is a different kind of shape. So what exactly is missing? A linear model can only form decisions by adding up weighted inputs once. It can stretch space, rotate it, shift it, but it cannot bend it. To solve XOR, you need the model to create a new feature like are both inputs the same, which is a kind of interaction. That interaction is not a weighted sum, it is a new computation. Here is the recompressed lesson. Linear models are not simple but weak in some vague way. They are models whose decision boundary is a hyperplane in whatever space you feed them. If the pattern is not separable by one hyperplane in that space, training cannot fix it. The only escape is to change the space, invent new features, or build a model that can bend the boundary. And that sets up the next invention. If a straight cut is too rigid, we need a way to build curved cuts while still using the tools we already trust, losses and gradient descent. The natural move is to keep linear pieces but stack them with a bend in between. In the next episode, we invent non-minus linearity, and we do it in the most minimal way possible.